Welcome back to VQ Intel. In this video, we're going to be working on removing discontinuities from functions. If you want to follow along, the links to the companion worksheets are down in the description. So each of these functions has a removable discontinuity that we want to remove. And when students ask me, how do you know where they exist? Usually I tell them that, well, if you plug in a value for x and you get 0 on the top and you get 0 on the bottom, that's a good sign. Now, what we're going to be using is some of the tools that we used in a previous video when we did finding limits involving factoring, involving conjugates, and involving trig identities. So if you want to, click in the upper right-hand corner of the video, and you can see those videos if you need to go over those first. Now this first one, we can rewrite it in factored form. X plus 3 times x minus 2 all over x plus 3. So we can clearly see that the removable discontinuity happens at x equals negative 3. And so when we cancel it out, when we simplify it, we get x minus 2. And what we can use that for is to figure out, okay, we want this to be continuous. So in order to be continuous, the limit has to exist. So the limit as x approaches negative 3 of this function, x squared plus x minus 6 all over x plus 3 is, well, if I plug in negative 3 in for x minus 2, I get negative 5. And so when I want to write this as a function that is continuous, I say, okay, I'm going to need to write it piecewise. First, I write the original function, and most often teachers and textbooks want you to write the original function, not the simplified version. Now, if your teacher or textbook does differently, I stand corrected. And then this function exists at every location where except where it's not continuous, which we identified was negative 3. And at the place where where the removable discontinuity takes place, we assign it this limit. So now this limit and this y value will now exist, and now writing it this way makes it continuous. So let's look at the next one. With this one, here I have 2 minus x, and then I factor this x minus 2 times x plus 2. So the location of our discontinuity, the removable discontinuity, is x equals 2. That's going to make the top 0 and the bottom 0. And if I cancel these out, I'm left with negative 1 over x plus 2. So the limit as x approaches 2 of 2 minus x over x squared minus 4, well, if I plug in 2 here, I get negative 1/4. So when I write this piecewise, I have 2 minus x over x squared minus 4, where x does not equal 2, and at x equals 2, we have negative 1/4. Now, one thing that some teachers may also have you do is to identify any other places where the function is not continuous, whether it's removable or not. And in this case, we have one other place where the function is undefined, and that is at negative 2. Now, that's a non-removable discontinuity, but some teachers, some books will say take that out as well. Now this one, number 3, can't be factored. Instead, what we have to do is we have to multiply by the conjugate. So square root of x plus 1 all over square root of x plus 1 plus 1. Now this is difference of squares, so we're going to have x plus 1 minus 1 all over x times the square root of x plus 1 plus 1, like that. And the top will simplify to x over x times the square root of x plus 1 plus 1. And the x's will cancel, so we have square root of x plus 1 plus 1. And so what we canceled out was we canceled out x and x, which means that's where the removable discontinuity took place. And so now the question becomes, all right, what's the limit? As x approaches 0 of this function, square root of x plus 1 minus 1 over x. So if I plug in 0 here, I get square root of 1 over square root of 1 plus 1, so I get 1/2. So when I write this, square root of x plus 1 minus 1 over x, when x does not equal 0. And then when x does equal 0, it's 1/2. The other thing to note is that we still have this radical of x plus 1. And in order to be defined, this has to be positive or 0. So that means x has to be greater than or equal to -1. So we also put this restriction in here. X is not equal to 0, and x is greater than or equal to -1. On the next page, here we have a conjugate, but this conjugate is in the denominator. So we're going to multiply square root of x plus 1 plus 2 over square root of x plus 1 plus 2. And in the denominator, we have x plus 1 minus 4. Then we have x minus 3 times this quantity, square root of x plus 1 plus 2. Now this will simplify to x minus 3, so that'll cancel out. So we're left with square root of x plus 1 plus 2. Now what canceled out? X minus 3. So that was our location for our removable discontinuity. So when x approaches 3, we need to figure out what was that value. What should it be in order to be continuous? So I can plug it in here. 3 plus 1 is 4, square root is 2, plus 2 is 4. So x minus 3 over square root of x plus 1 minus 2 when x does not equal 3. When x does equal 3, we want it to assign it this value. And as before, we have x plus 1 under the radical. So like the last one, x has to be greater than or equal to -1. So here with this one, I'm going to focus on just the numerator. 1 over x plus 5 minus 1/5. So I need a common denominator. So it's going to be 5 times the quantity x plus 5. And when I subtract these, remember it's 5 minus 5, and I'm still subtracting x. So negative x over 5 times x plus 5. Now I want to cancel out the x. So I'm going to factor out x. So I'm left with -1 over 5 times x plus 5. So when I substitute this back over, I have x times the quantity -1 over 5 times x plus 5. And now I can see that the x's cancel, and I'm left with -1 over 5 times x plus 5. So my location for my removable discontinuity was 0. That's what was canceled out. So I want to find the limit as x approaches 0. 1 over x plus 5 minus 1/5 all over x. Well, that's the same as plugging 0 in here. Okay. So 0 plus 5 is 5 times 5 is 25. So it's -1 over 25. So when I write this without the discontinuity, I have 1 over x plus 5 minus 1 over 5 all over x. When x does not equal 0, when x does equal 0, it has to have that value in order for it to be continuous. Now with this problem, after we simplify, notice that we still have x plus 5 in the denominator, which we can't have, at least not when x is -5. So we have to exclude that from the domain if we want to exclude all discontinuities. So number 6, here we have a trig. And so when trig is involved with sine, we know that it's x equals 0. So to make this work, I'm going to write this as sine of 4x over 4x, but I need to cancel out the 4 that was there, so that's multiplied by 4 over 1. So the limit, as x approaches 0, of sine of 4x over 4 over x, well, this is going to become 1 times 4, so that means the limit will equal 4. So when I write this as continuous, I have sine of 4x over 4 when x does not equal 0. And when x equals 0, I want it to equal, whoops, that should be x, not 4, when x equals 0. And then finally down here, very similar, but here I want to pull out the 2, times 2, and I want there to be a 3. So 3x over sine of 3x times 2 times, and I have to cancel out that 3, so times 1/3. So now this limit will be undefined. This will be undefined when x equals 0. And the limit as x approaches 0 of 2x over sine of 3x is 2/3, because this is 1 times 2 times 1/3. So when I write this, we have 2x over sine of 3x when x does not equal 0. When x does equal 0, it is 2/3. Now, one last thing to notice is that sine of 3x is in the denominator. So that means sine of 3x cannot equal 0. Well, let's think about it. When does sine equal 0? Sine equals 0 at, let's see, sine of x equals 0 when x is 0, pi, 2 pi, 3 pi, and so on. So that means that whatever 3x is, it cannot be n pi, where n is an integer. And then if I get x by itself, I'm going to divide by 3. So I also have to put over here, x cannot equal n pi over 3, where n is any integer. Thanks for watching. If you like this video, give it a thumbs up. If you want to support the channel, links are down below. Remember, in all that we do, the best way to understand something is to do it.